Let us come to Newton's second law. As per Newton's second law, when observed from an inertial frame, net external force acting on an object is equal to product of its mass and acceleration, or much more simply, F is equal to ma. There are few points about Newton's laws of second law which I want to discuss. The first is, the condition for inertial frame is still there. Newton's first law and second law depend on frame being inertial. The second is, this is a vector law. What does that mean? Force is a vector, acceleration is a vector. When we apply this law, we will have to take care of rules of vector algebra. There are two more things. Ignore this point. As per many teachers, the correct form of Newton's second law is, when observed from an inertial frame, net unbalanced force acting on an object is equal to rate of change of momentum. Rather than saying F is equal to ma, many teachers say that the correct form is F is equal to rate of change of momentum, dp by dt. They are correct. But the point is, F is equal to ma is much more simpler. And both these forms are identical in most of the cases. Both these forms are identical as long as the system we are studying is having constant mass. We are just starting with laws of motion. Initially, we are only going to study systems which are having constant mass. So we are going to apply F is equal to ma in all cases. Later on, when we are through, we are confident about laws of motion, then I will tell you how do we handle variable mass system. But before that, I am just going to prove that both these forms are identical, but ignore this part in the beginning. You can come to this part later on. Many teachers, the correct form of Newton's second law is F is equal to dp by dt, where P is momentum. What is momentum? Momentum is P is equal to mv. We are going to prove that this form of Newton's second law is identical to the form F is equal to ma. How will we do that? We will pick this P and put it over here. What will that give us? That will give us F is equal to dmv by dt. Now next, what we are going to do is, we are going to take this m outside the differentiation. We can do that if m is constant. When we do that, we will get F is equal to m dv by dt. Now we know that dv by dt is acceleration. That gives us F is equal to ma. That proves that this form and this form of Newton's second law are identical. The only case where we cannot do that is when m is variable. If m is variable, then taking it outside differentiation is not possible. Product rule will be applicable. Initially, in all our problems, mass will be constant, and we are going to apply this form of Newton's second law. There are few more points about Newton's first law and second law I want to discuss with you. However, these points are tougher, so you can skip. These points are required if you want a strong theoretical understanding of Newton's laws. However, these points are not really required if you just want to get started with Newton's laws. That is, you just want to start solving the problems. So, and these points are tougher, so it might be a good idea to just listen to this once, skip it, come back to it later on, and then think deeply about it. Here is an object which is at rest. It might be moving with constant velocity also. There are 3 or 4 forces acting on it from different sides. I am going to discuss cause and effect with you. Which statement is more correct? Net force acting on the object is 0. As a result, this object is at rest. The other statement is, this object is at rest, hence net force acting on it is 0. As per Newton's first law, the correct statement is, this object is at rest or moving with constant velocity, that is inertial. Hence, by definition, net force acting on it has to be 0. Think about it. If there is no force acting on it on an object, that is, no one is pulling it, no one is pushing it, then we can say that net force is 0 because there is no force at all. But suppose there are multiple forces acting on an object, then how do you know that net force is zero? And the solution is, we know it through Newton's first law. As per Newton's first law, if an object is inertial, then by definition net force on it has to be zero. Without help of Newton's first law, there is no way to define a state, no way to calculate when force is zero. Newton's second law defines force. We define force as a push or a pull. However, that definition, a push or a pull, is not sufficient for calculating force. Then how do you calculate force? The only way of calculating force is Newton's second law. Force is what causes acceleration. So if this object is accelerating, there must be a force on it. Think about it. Think about it deeply. These points are slightly tougher. Newton's third law is same as what you have studied in earlier classes. Action and reaction are equal and opposite. There is an alternative language for Newton's third law. All forces exist in pairs which are equal and opposite. First thing, there is no condition for inertial frame. Second thing, here is a simple example for Newton's third law. Here is my pen stand. I am applying a force on it. The force that I am applying on pen stand is in this direction. As a result, the pen stand will also apply a force on my hand in this direction. These forces are action-reaction pairs which are equal and opposite. There are few misconceptions about Newton's third law. Let us discuss them one by one. The first one is, if I am applying a force on this pen stand and as a result pen stand is applying a force on my hand, which one of the force is action and which one of the force is reaction? Obviously, the force that I am applying on the pen stand is going to be action. The force that pen stand is applying on my hand is going to be reaction. Incorrect. The correct concept is, either of these forces can be action, either of these forces can be reaction. Why did we say that the force I am applying on the pen stand is action? Because I am a living being. So I decided that I am going to apply this force. I am the cause. However, living being and non-living beings come in biology. In physics that we are studying, they don't really play any role. What will you do if two machine parts are pushing each other? Or alternatively, as you can see, I am pushing one of my hand with other hand. In this case, both the hands came together. Both the hands are pushing each other. Which one of the force is action? Which one of the force is reaction? The correct concept is, either one of the force can be action, the other will automatically become reaction. Another thing, action and reaction forces must have same fundamental nature. In this case, the force I applied on the object and the force object applied on my hand, both were normal forces. Normal forces are electromagnetic, so they had same fundamental nature. Another thing, if action force is being applied by object A on object B, then reaction force will have to be applied by object B on object A. Action and reaction forces are always applied on contrary parts. It is not possible that both action and reaction forces are acting on the same objects. With these points in mind, let us look at few examples of action-reaction pairs. Let's look at this example and analyze action-reaction forces. I am standing in front of you. What forces are acting on me? In downward direction, mg is acting due to gravity. In upward direction, ground is applying a force on my shoes. This force is this normal force. Since I am stationary, net force on me must be zero. This is only possible when normal and mg are equal and opposite. That means normal and mg should be action-reaction pair. Wrong. This is a common misconception. Normal and mg cannot be action-reaction pair due to multiple reasons. Number one, they do not have same fundamental nature. Normal is electromagnetic in nature, whereas mg, weight, is gravitational in nature. Moreover, in this, if I jump, normal will disappear. Mg will still remain there and they will not remain equal and opposite. What is more, in this case, both normal and mg are acting on me. what we had discussed was, if A applies a force on B and that is action, reaction will be applied by B on A. In this case, both normal and mg are acting on me. As a result, these two forces are not action and reaction pair. So where are action and reaction pairs? Look at this example. Here, ground is applying normal on my shoes. I am applying normal on ground. These are action-reaction pairs. Both are electromagnetic. If one force is being applied by me on the ground, the other force, the ground is applying on me. Moreover, if I jump, both these forces will disappear simultaneously. But where is the reaction force for gravitation? For that, we will have to step back a bit. This is Earth. I am standing over here. mg is acting on me in downward direction. mg is also acting on ground in upward direction. These are action-reaction pairs. After all, Newton did ask, when an apple falls down, why doesn't the earth rise up? The answer is, the force that acts downward on apple also acts upward on earth. That force is a large force for the apple. As a result, it falls down. That force is negligible for earth. As a result, nothing happens to it.